TTL Computer 2. So today we're going to take a look at our control circuit for TTL Computer 2. And just a refresher that the control circuit is really the brains, I'll say, of the whole CPU. And using in combination with the tick counter and our clock circuit, that this really synchronizes everything that happens within the computer. It raises and lowers all of our control signals that makes all of the data move around in specific ways between different registers in the computer. And this is really where, in combination with the microcode, this is kind of where the magic happens in the computer to give it all of its brains. So you can see that we have three main chips in our control circuit. And these are three 8K ROMs. And we will be utilizing every byte within each of these ROMs for the control data for our computer. Okay, so each of these ROMs are all wired in parallel. So all of the input signals that go to one of the ICs are the same input signals that go to, all three of the ICs. What differs, however, is the data that comes out. The data that comes out, each of the ICs for a given address is different. And this will be, eight control bits will come at it. For a given address, 8 control bits will come out from ROM 1. The next 8 control bits will come out from ROM 2. And then the next 8 control bits will come out from ROM 3, all for the same given address. But, combining those together gives us our 24-bit control signals. Okay, so since the address is so important here, I'm going to zoom in here and look at how we construct that address. So the lowest 4 bits of the address, we have address A0 all the way through A12. So the lowest 4 bits of the address come from the tick counter. The next higher 3 bits come from our flags, the 0, the C, and the negative flag. And then the top 6 bits, A0, 1, 2, 3, 4, and 5, come from our opcode. And those makes up the highest 6 bits in the address space. Okay, so that's how that is used. And I'm going to switch over here to my program that actually generates the ROM file, and you can kind of see how this is used. All right, so we're all the way down at instruction 38. So there's a whole bunch of instructions that precede it. But what I want to show you here is how each instruction requires 8 control records, right? And we can see that here are our bits, right? The Z, the C, and the N flag. So, right, so this is instruction 38. That opcode sets the high 6 bits in the address, and then these set the next 3 lower bits, and then the tick sets which of these, right? There's 16 ticks in the tick counter, and we have 16 bytes here per row. So we can see here, again, these are all of the combinations. These are all the combinations for our flags. And so this is the 16 byte control record for, right, not 0, not carry, not Z. And then this is the next 16 bytes for, the 0 flag set. And this is the next 16 control bytes for the carry flag set, and so on. And you see that this is just a straight jump, an unconditional jump. So all of these records are all the same, irregardless of the flags. But Down here, you can see that this is jump if not carry. So we can see here, here's our carry bit, that the 16-byte microcode steps differ in the case when the carry flag is clear, or a case when the carry flag is set. Right, so that's just a view on how that works and is organized, but that shows us how the ROM address space is used. Okay, so as I said, each of the ROMs receives the same input address, but the output, the 8-bit output, is different for each ROM, and each ROM outputs, 8 of the signals of our 24 control signals, and we can see here that the signals come out in their appropriate state, whether they're active low or active high. So the signals come out, as needed for TTL Computer 2. Now, we have some extra processing that we need to do here. We had to go through some gyrations to stick within the 24 control lines. And you can see down here that what we really need 6 control signals here for our program counter and for our memory address register. We need counter out high, memory in high, counter out low, counter in high, counter in low, and memory in low. So those are 6. But we only have 4 signals that we can use: counter out, memory in, counter in, and a high signal. So that's 4 signals that we have coming out of the ROM, but we need 6. So what we do is we do a little bit of extra processing here, where we take that high signal and we invert it, and that gives us our low signal. And then we have, we process, if it's counter out and high, right? Counter out and high, then we have counter out high. If it's counter out and our low signal, then we have, counter out low. And then the same thing for the memory address register. So in that way, with this extra logic, we saved 2 control signals, right? So we started with 4, but we end up with 6. Okay, so that's a little bit of extra logic that we put in, decode logic, I guess you would say, to save some control lines. Okay, but this in totality gives us our 24 control signals, right? Given our address inputs that we have. Okay, so a little complicated. There's a lot going on here, and if you think about it, it's pretty straightforward though. Okay, so for our next video, I think we will look at our ALU circuit for TTL Computer 2. And that's it for today. Thanks for watching.